Beneath the calm waters of Lake Toba on the Indonesian island of Sumatra, a massive supervolcano is lurking. This geological monster is one of only a handful of volcanoes capable of producing a super eruption that could catastrophically change the global climate system for decades. So how can we predict the next supervolcano eruption? This is a map of Indonesia. Officially the Republic of Indonesia, a country in Southeast Asia and Oceania between the Indian and Pacific Oceans. Indonesia consists of over 17,000 islands including Sumatra, Java, Sulawesi, parts of Borneo and New Guinea. Sumatra is the third largest island of Indonesia, and in the northern district North Sumatra is Lake Toga located, a large natural lake occupying the caldera of a supervolcano. Possibly the greatest volcano on Earth. Besides this supervolcano, the whole geography of Indonesia is dominated by volcanoes that are formed due to subduction zones between the Eurasian Plate and the Indo-Australian Plate. Some of the volcanoes are notable for their eruptions, for instance, Krakatoa for its global effects in 1883, the Lake Toba caldera for its supervolcanic eruption estimated to have occurred 74,000 years before present, which was responsible for 6 years of volcanic winter. Volcanoes in Indonesia are part of the Pacific Ring of Fire, also known as the Circum-Pacific Belt, is a region around much of the rim of the Pacific Ocean where many volcanic eruptions and earthquakes are occurring. The Ring of Fire is not a single geological structure. Volcanic eruptions and earthquakes in each part of the Ring of Fire occur independently of eruptions and earthquakes in the other parts of the ring. The Ring of Fire contains approximately 850 to 1,000 volcanoes, about 2/3 of the world's total, that have been active during the Holocene. The 4 largest volcanic eruptions on Earth in the Holocene epoch all occurred at volcanoes in the Ring of Fire. The most active volcano in Indonesia is Mount Merapi on Java. Since AD 1000, the Kellet volcano has erupted more than 30 times, of which the largest eruption was at scale 5 on the Volcanic Explosivity Index, VEI, while Mount Merapi has erupted more than 80 times. The International Association of Volcanology and Chemistry of the Earth's interior has named Mount Merapi as a decade volcano since 1995 because of its high volcanic activity. As of 2012, Indonesia has 127 active volcanoes and about 5 million people living within the danger zones. It has been conjectured that the earthquake and tsunami event of the 26th of December 2004 could trigger eruptions, with Mount Sinabung, dormant since the 1600s, erupting in 2010 as a possible example. The word for mount in Indonesian and many regional languages of the country is Gunung. Thus, Mount Merapi may be referred to as Gunung Merapi. However, there is no single standard definition for a volcano. It can be defined from individual vents, volcanic edifices, or volcanic fields. Interior of ancient volcanoes may have been eroded, creating a new subsurface magma chamber as a separate volcano. Many contemporary active volcanoes rise as young parasitic cones from flank vents or at a central crater. Some volcanic cones are grouped into one volcano name, for instance, the Tengah Caldera complex, although individual vents are named by local people. The status of a volcano, either active or dormant, cannot be defined precisely. An indication of a volcano is determined by either its historical records, radiocarbon dating, or geothermal activities. The geography of Sumatra is dominated by a mountain range called Bukit Barisan, which translates to a row of hills. The mountain range spans nearly 1,700 kilometers, 1,100 miles, from the north to the south of the island, and it was formed by movement of the Australian tectonic plate. The plate moves with a convergence rate of 5.5 centimeters per year, which has created major earthquakes on the western side of Sumatra, including the 2004 Sumatra Andaman earthquake. The tectonic movement has been responsible not only for earthquakes, but also for the formation of magma chambers beneath the island. Only one of the 35 active volcanoes, Way, is separated from the Sumatran mainland. The separation was caused by a large eruption that filled the lowland between Way and the rest of the mainland with seawater in the Pleistocene epoch. The largest volcano of Sumatra is the supervolcano Toba within the 3,000 square kilometer or 1178 square miles Lake Toba, which was created after a caldera collapse in 74,000 before present. The eruption is estimated to have been at level 8 on the VEI scale, the highest level for a volcanic eruption. The highest peak of the mountain range is Mount Kerinci with an elevation of 3,800 m, or 12,467 feet. Anak Krakatau is one of those volcanic islands in Indonesia. On the 29th of December 1927, the Anak Krakatau volcano first emerged from the caldera formed in 1883 by the explosive volcanic eruption that destroyed the island of Krakatau. The 1883 volcanic eruption of Krakatau in the Sunda Strait occurred from the 20th of May 1921 October 1883, peaking in the late morning hours of the 27th of August, when over 70% of the island of Krakatau and its surrounding archipelago were destroyed as it collapsed into a caldera. This volcanic eruption was one of the deadliest and most destructive volcanic events in recorded history. The explosion was heard 3,110 kilometers, or 1,930 miles, away in Perth, Western Australia, and Rodrigues near Mauritius, 4,800 kilometers, or 3,000 miles, away. The sound of the volcanic eruption was reportedly heard in 50 different locations around the world, and the volcanic sound wave is recorded to have traveled around the globe 7 times. At least 36,417 deaths are attributed to the volcanic eruption and the tsunamis it created. Significant additional effects were also felt around the world in the days and weeks after the volcano's eruption. Additional seismic activity was reported until February 1884, but any reports after October 1883 were later dismissed by Roger Verbeek's investigation into the eruption. The combination of pyroclastic flows, volcanic ash, and tsunamis associated with the Krakatau eruptions had disastrous regional consequences. Some land in Banten, approximately 90 kilometers south, was never repopulated. It reverted to jungle and is now the Ujung Kulon National Park. The official death toll of the eruptions recorded by the Dutch authorities was 36,417. Ships as far away as South Africa rocked as tsunamis hit them, and the bodies of victims were found floating in the ocean for months after the event. The tsunamis which accompanied the eruption were believed to have been caused by gigantic pyroclastic flows entering the sea. Each of the 4 great explosions was accompanied by large pyroclastic flows resulting from the gravitational collapse of the eruption columns. This caused several cubic kilometers of material to enter the sea, displacing an equal volume of seawater. The town of Merak was destroyed by a tsunami which was 46 meters high. The 1883 Krakatau eruption darkened the sky worldwide for years afterwards and produced spectacular sunsets throughout the world for many months. British artist William Ashcroft made thousands of color sketches of the red sunsets halfway around the world from Krakatau in the years after the eruption. The ash caused such vivid red sunsets that fire engines were called out in New York, Poughkeepsie, and New Haven to quench the apparent conflagration. This eruption also produced a bishop's ring around the sun by day, and a volcanic purple light at twilight. In 2004, an astronomer proposed the idea that the red sky shown in Edvard Munch's 1893 painting The Scream is also an accurate depiction of the sky over Norway after the eruption. Weather watchers of the time tracked and mapped the effects on the sky. They labeled the phenomenon the equatorial smoke stream. This was the first identification of what is known today as the jet stream. For several years following the eruption, it was reported that the moon appeared to be blue and sometimes green. This was because some of the volcanic ash clouds were filled with particles about 1 micrometer wide, the right size to strongly scatter red light, while allowing other colors to pass. White moonbeams shining through the clouds emerged blue, and sometimes green. People also saw lavender suns and, for the first time, recorded noctilucent clouds. There has been sporadic eruptive activity at the site since the late 20th century, culminating with a large underwater collapse of the volcano that caused a deadly tsunami in December 2018. There has been subsequent activity since. Due to its young age, the island is one of several in the area that are of interest to, and the subject of extensive study by, volcanologists. After the cataclysmic eruption of Krakatau in 1883, Krakatau Island lost approximately 2/3 of its body on the northwest side, obliterating the peaks of Pabuatan and Danan, and leaving only the southern half of the island, including the Rakata volcano, as the last remnant of the original island. The lost area became a shallow sea. An eruption of the volcano on the 22nd of December 2018 caused a deadly tsunami, with waves up to 5 meters in height making landfall. On the 31st of December 2018, the disaster agency stated the tsunami's death toll was 437, with 14,059 injured. The tsunami affected more than 300 kilometers, 186 miles, of coastline in Sumatra and Java, and 40,000 people were displaced. This made the eruption the second deadliest volcanic eruption of the 21st century to date. Cone collapse, with tsunami generation, was considered a potential hazard immediately before the eruption. Scientists had modeled the possibility 6 years before the event and had identified the western flank as the section of the volcano most likely to fail. Following the December 2018 eruption, it was believed that the southwest sector of the volcano, including the summit, had collapsed during the eruption, triggering the tsunami. On the 23rd of December, this was confirmed by satellite data and helicopter footage, with the main conduit seen erupting from underwater, producing Science-style activity. The volcano lost over 2/3 of its volume due to this event, and its elevation above sea level was reduced from 338 meters (1,109 feet) to just 110 meters (360 feet). Satellite radar observations showed that by the 10th of January 2019, the volcano had continued to form, with further eruptions beginning to remodel the remnant structure. The crater, which had become open to the sea immediately after the eruption, had a complete rim above sea level. In May 2019, phreatomagmatic activity was observed around the newly reconstructed crater as the volcano continued to increase in height and remodel the areas destroyed in 2018. Since then, the Krakatoa volcano had 2 more small eruptions in 2020 and 2022. But although here we already can see how powerful nature can be, it is with no doubt not comparable to the massive supervolcano at Lake Toba. The youngest Toba eruption was a supervolcano eruption that occurred around 74,000 years ago at the site of present-day Lake Toba in Sumatra, Indonesia. It is one of the Earth's largest known explosive eruptions. The Toba supervolcano catastrophe theory holds that this event caused a global volcanic winter of 6 to 10 years and possibly a 1,000-year-long cooling episode. In 1993, science journalist Anne Gibbons posited that a population bottleneck occurred in human evolution about 73,000 years ago, and she suggested that this was caused by the eruption. Geologist Michael R. Rampino of New York University and volcanologist Stephen Self of the University of Hawaii at NOAA support her suggestion. In 1998, the bottleneck theory was further developed by anthropologist Stanley H. Ambrose of the University of Illinois Urbana-Champaign. However, both the link and global winter theories are controversial, but the youngest Toba volcano eruption is the most closely studied supervolcanic eruption. The youngest Toba supervolcanic eruption occurred at the present location of Lake Toba in Indonesia, about 74,000 years BP according to potassium-argon dating. This eruption was the last and largest of 4 eruptions of the Toba caldera complex during the Quaternary period, and is also recognized from its diagnostic horizon of ashfall, the youngest Toba tuff. It had an estimated volcanic explosivity index, VEI, of 8, the highest rating on the scale. It made a sizable contribution to the 100 kilometers 35 kilometers, 62 miles 22 miles caldera complex. Dense rock equivalent, DRE, estimates of eruptive volume for the eruption vary between 2,000 cubic kilometers, or 480 cubic miles, and 3,000 cubic kilometers, or 720 cubic miles. The most common DRE estimate is 2,800 cubic kilometers, or 670 cubic miles, of about 7x 10 to the power of 15 kilograms, 1.5 10 to the power of 16 pound of erupted magma, of which 800 cubic kilometers, or 190 cubic miles, was deposited as ashfall. The erupted mass was, at the very least, 12 times greater than that of the largest volcanic eruption in recent history, the 1815 eruption of Mount Tambora in Indonesia, which caused the 1816 year without a summer in the northern hemisphere. Toba's erupted mass deposited an ash layer of about 15 centimeters 6 in thick over the whole of South Asia. A blanket of volcanic ash was also deposited over the Indian Ocean, the Arabian Sea, and the South China Sea. Deep sea cores retrieved from the South China Sea have extended the known reach of the volcanic eruption, suggesting that the 2,800 cubic kilometers or 670 cubic miles calculation of the erupted mass is a minimum value or even an underestimate. Based on new methods, computational ash dispersal model using a 3D time-dependent tephra dispersion model, a set of wind fields, and several tens of thickness measurements of the YTT tephra deposit, the Toba caldera complex possibly erupted as much as 13,200 cubic kilometers in total bulk volume. This has led to some sources labeling the youngest Toba eruption as a VEI 9 event. Geologist Michael R. Rampino and volcanologist Stephen Self argue that the volcanic eruption caused a brief, dramatic cooling or volcanic winter, which resulted in a drop of the global mean surface temperature by 3 to 5 degrees Celsius, or 5.4 to 9.0 degrees Fahrenheit. Evidence from Greenland ice cores indicates a 1,000-year period of low delta O18 and increased dust deposition immediately following the eruption. The eruption may have caused this 1,000-year period of cooler temperatures, 2 centuries of which could be accounted for by the persistence of the Toba stratospheric loading. Rampino and Self believe that global cooling was already underway at the time of the eruption, but that the process was slow. The youngest Toba tuff may have provided the extra kick that caused the climate system to switch from warm to cold states. Although Clive Oppenheimer rejects the hypothesis that the volcanic eruption triggered the last glaciation, he agrees that it may have been responsible for a millennium of cool climate prior to the 19th Dansgaard-Oshkosh event. According to Alan Robock, who has also published nuclear winter papers, the Toba eruption did not precipitate the last glacial period. However, assuming an emission of 5.4 billion tons, 6 billion short tons of sulfur dioxide, his computer simulations concluded that a maximum global cooling of approximately 15 degrees Celsius, 27 degrees Fahrenheit occurred for 3 years after the eruption, and that this cooling would last for decades, devastating life. Because the saturated adiabatic lapse rate is 4.9 degrees Celsius per 1,000 meters or 2.7 degrees Fahrenheit per 1,000 feet, 4 temperatures above freezing, the tree line and the snow line were around 3,000 meters, 9,800 feet, lower at this time. Despite these different estimates, scientists agree that a supervolcanic eruption of the scale at the Toba caldera complex must have led to very extensive ashfall layers and injection of noxious gases into the atmosphere, with worldwide effects on weather and climate. In addition, the Greenland ice core data display an abrupt climate change around this time, but there is no consensus that the eruption directly generated the 1,000-year cold period seen in Greenland or triggered the last glaciation. We told you about the calm waters of Lake Toba where a massive supervolcano is located. The question is though, how can we predict the next supervolcano eruption? An international team of geologists has investigated the potential early warning signs of such a world-shaking eruption, focusing on the volcano beneath Lake Toba. This volcano has produced 2 of the most massive eruptions the Earth has ever seen, occurring 840,000 years ago and 75,000 years ago. Each produced enough ash to blanket the whole of Switzerland with 7 centimeters of ash. There has been no equivalent-sized volcanic eruption in recorded human history, so this research is crucial to informing how we might be affected and how we might respond. The new study, published in PNAS, measures how long it took for the Toba volcano to build up its magma reservoir in the lead up to these 2 past super-eruptions. Magma is what makes supervolcanoes so dangerous. The molten rock builds up and up in the mantle below the crust, unable to break through, until the pressures become so great that the whole system explodes. The good news? The researchers think that Toba's next major supereruption is still 600,000 years away. The bad news? The eruption won't be heralded by weird geological signs. In fact, we won't know when it's coming. The buildup will be slow and silent. To come to these conclusions, the team analyzed the levels of uranium and lead in zircons, a tiny crystal found in volcanic rocks. Previous research has shown that zircons can be used to estimate the volume of magma stored below volcanoes. One of its characteristics is that it takes uranium within its structure, says lead author Pingping Liu from Peking University in China. She explains that over time the uranium decays into lead, so by measuring the amount of uranium and lead in zircon with a mass spectrometer, we can determine its age. The team dated zircons from a number of different Toba eruptions, where the youngest zircon indicates the date of the eruption and older ones indicate how magma has built up. The first supereruption occurred around 840,000 years ago, after 1.4 million years of magma input, whereas magma fed the second supereruption at 75,000 years accumulated only in 600,000 years, says Luca Caricchi, co-author from the University of Geneva, Switzerland. The eruptions were the same size. The researchers say that the second eruption built up its magma more quickly because over time, magma heats up the continental crust around the volcano, which keeps the magma hot for longer. This is a vicious circle of eruptions. The more the magma heats the crust, the slower the magma cools and the faster the rate of magma accumulation becomes, says Pingping Liu, meaning that supereruptions can become more frequent as time goes on. This zircon dating technique allowed the team to estimate how much magma is simmering below the surface of the volcano. Today, we estimate that about 320 cubic kilometers of magma could be ready to erupt within the reservoir of Toba volcano, says Kariki. This wouldn't be classed as a super eruption, which needs to be greater than 1,000 cubic kilometers and would definitely be smaller than the 2,800 cubic kilometers spewed out in Toba's two big eruptions, but it's still enough to create massive global disturbance. The researchers say that an extra 4 cubic kilometers of magma builds up in Toba every 1,000 years. This means that next equivalent supereruption would occur in 600,000 years, though smaller ones could happen in the meantime. This method could also be applied to other supervolcanoes around the globe, like Yellowstone in the US. Our study also shows that no extreme events occur before a supereruption, adds Kariki. This suggests that signs of an impending supereruption, such as a significant increase in earthquakes or rapid ground uplift, might not be as obvious as pictured in disaster movies by the film industry. At Toba volcano, everything is happening silently underground, and the analysis of the zircons now gives us an idea of what is to come. Ultimately, this means we can never be certain if or when the next supervolcanic eruption will happen, but what is certain is that humanity and the world we live in will never be the same. After such a massive super eruption, tell us in the comments which supervolcano you think is the more powerful and most dangerous one for the world and humanity. Yellowstone or Toba volcano?